Hello everyone, welcome to the last reading group of the quarter. Today we're going to be talking about generative models, AI art, and beyond. How we push Stable Diffusion to its limits. For those of you who attended my reading group last quarter, I focused a lot on what led up to diffusion models and the formalisms of diffusion models last time. But this time we're going to focus a lot more on the applications. So what people have done, taking Stable Diffusion and applying it to a lot of different applications and to a lot of different tasks that's just beyond the humble text prompts. So before we get started, I actually want to just give you a super duper quick overview of what diffusion models are and how we actually mostly do text to image generation nowadays. So what we're essentially doing, what these diffusion models are doing is they're essentially mapping noise or some easily generatable distribution to image, something that is really, really difficult to generate, right? And it does so iteratively. Particularly, the way you generate an image is you give it, the image generators a bunch of noise. You know, this noise is very easy to generate Gaussian noise. Our computers can do it very easily. And what you're doing is essentially passing it through the network. An image will come out that's just with slightly less noise to it. You pass the image back to the generator. It gets rid of a bit more noise. You pass it back again, gets rid of a bit more noise. And you do this iteratively until the image you get out is completely clean. Right? So essentially, a good way to think of diffusion models is a model that is so good at denoising, it is able to generate images or really just any distribution of data from noise, right? It is able to denoise from nothing. And there's a lot of, and there's a lot of ways that this has impacted, the art worlds, the ML worlds. But though this is a pretty good overview, it actually hides a lot of things. The first thing is, what's going on here with the text encoder? How do we actually inject this in? What is the image generator? Why is the model able to do the denoising? Does it have to be iterative? And isn't this very expensive that we have to do this iteratively? That's what we're going to answer today. So, to go over what we're going to be talking about today, this presentation is kind of divided into 3 parts. First part, controllable generation. Second part, beyond 2D images. And the third part, more than a generator. So, I've given you the overview. At this point, you should be very familiar with text-to-image models, right? This makes perfect sense to you. I'm assuming? No. So we're going to have a part 0, right? Text-to-image models. So this, we're actually going to build up the foundation of what Stable Diffusion is and all the other paradigms of text-to-image models that people came up with. So, to be able to start in that section, I assume you are familiar with diffusion models in general, right? It's pretty good. Okay, so part -1, we're going to talk about diffusion models as well. But to know about diffusion models, you have to have a pretty good understanding of the current landscape of generative vision. So about this stuff, VAEs and whatnot. Okay, so we're going to start from part -2. How did we get here? So before we even begin, I want to talk about what is generative vision. So far, if you were, say, in advanced track or a lot of different, or other workshops and whatnot, where you have done some projects, what you have probably been doing is discriminative modeling, which is the idea of we're trying to learn Py of X. What that's really saying is the probability that image X is the label Y, right? Because that's what the output distribution is. That's what we do softmax. We do probability distribution, yada, 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 right? And the thing with discriminative modeling, especially with image classification, is that a lot of people say it's largely a quote unquote solved issue because, if you think about it, in ImageNet 2015, ResNet, right? That has already surpassed human performance, and we're kind of reaching a plateau of we're at 99 point something per person accuracy. We can't really get any better. So it's really just about scaling up at this point. So there is a shift in research over the years to generative modeling, where instead of learning the probability that the image belongs to some label, we're instead just learning the image distribution itself. Because if we were to be able to mathematically represent the distribution of a bunch of images, then there's no point in us, using a machine learning model, right? So the problem is always the data distribution is very, very, very difficult for us to figure out what it is. It's very, very difficult for us to approximate. So we're trying to use a machine learning model to learn that. And to generate an image is the same as sampling from this distribution. And we can also condition this distribution with stuff. For example, what is the distribution of images given that the text prompt is, an astronaut riding a pig, right? So you can see how if we were to give it this specific prompt, the distribution of output images, the total space of what images this model can generate is a little bit different. And the important thing is the data set is not the distribution. The data set is only samples of the distribution that we can use to represent it but we can never truly represent what the space of all images that humans call, cool, that's a good enough looking image be, right? That's very difficult to define. So we can use datasets to help us. So the very first-ish attempt at generative vision is something called a variational autoencoder. And what it is it's from this paper in 2013. By the way, the slides, that it is all in the asset cluster. You can find the slides there. We have 74 slides today. So there's a lot. So definitely follow along and click into the papers if you are interested. But basically, the idea of an autoencoder is that we're trying to compress information. The goal of this is we have some really high dimensional, say, an image, inputs. We're passing it through this encoder that compresses it down to a much lower dimensional data, and we're trying to reconstruct that data with a decoder. So we're basically, our loss will be, the difference between our input and reconstruction has to be very, very small. So what this does is it creates a latent space, a representation of our inputs that is much more compressed. So you may start to see, hey, if we can somehow generate just this tiny bit of the latent space here, we'll be able to just generate a bunch of images. But the problem is, this latent space is very hard to sample from. Because we still don't know the distribution of this latent space. It's just like a bunch of vectors in a very specific distribution of things. So to make this latent space actually sampleable, this is where variational autoencoders come in. In short, it basically does this like regularization thing. So instead of calculating the latent space directly, it calculates the HNG, so like the mean and standard deviation of the latent space given the input image. So what you can do is then pass in like a mean of all the data, figure out the mean of the mean and standard deviation, and then like sample it with noise. Basically, it makes it so that we can sample from the middle. Right? Yes?
Why don't you just use variational inference on the autoencoder?
Oh, like on this itself?
Yeah.
Because the thing is, if we were to just pass in because the thing is, what the original autoencoder is, there is a direct one-to-one mapping, one-to-one-ish mapping between our input and this thing in the middle, right? Which means whatever we pass in here, there's no way for us to vary this around so that we can get different outputs. So the point is that we're trying to get different outputs. So this noise here that we're essentially injecting into the latent space is helping us do that. And at the time, what people found out is that the latent space in the middle is actually smooth, so you can kind of like interpolate between them. And even though the results look like absolute trash in today's standards, people are really excited by this, right? Because this is the first example of like, hey, we're generating stuff. And later someone figured out VPVAEs, which is like vector quantized variational autoencoders, which is like the latent space to keep like this dictionary of things, kind of like vector embeddings, but not really. We're not going to get into it today. But the idea is that this is kind of the quote-unquote ceiling of where VPVAE is now. And it's not bad, but it's kind of limited to like, say, just one type of data, like faces or like cats or like, sometimes you can condition it with classes like on ImageNet. But that's kind of where we have stopped for VAEs. Then we come to generative adversarial networks, which is still, in my opinion, one of the greatest things to ever come out in 2010's machine learning. So the idea of a generative adversarial network is like you're actually training two models at once. A generator, which its goal is to take in some random noise, right? Really low dimensional random noise, and just generates a fake image out of it, via a bunch of transpose convolutions to inflate this noise up. And we have a discriminator, which takes in either a real image or a fake image, the real image in this case referring to image coming from our actual data sets, and it tries to discriminate or tries to tell whether the image that has passed into it is real or fake. So it's basically a binary classifier. And we're training these two models jointly in a way it's adversarial because their loss, as you can see, are kind of like directly against each other. The generator wants to fool the discriminator, but the discriminator wants to figure out what the generator is doing, right? So if we just, pass gradients through each other, basically what people found is that the theoretical optimum or the theoretical like minimum of like loss for the generator is the generator will eventually move, like the output distribution generator will eventually move to be the same as our data distribution, because that's the way for it to reach its minimum. So theoretically speaking, at least, generative adversarial networks are really, really good because instead of trying to calculate the distribution directly, we're basically using discriminator to coerce the generator into generating our data, right? So the effects of that is actually really, really good. So this is, as you can see here, like this is kind of like the thing that made GANs like really, really good, which is a paper called Style GAN. Has everyone seen here, this person does not exist.com? Right? So like if you actually were to go to this website, basically it just generates a picture of a person that, does not exist. And it's actually from StyleGAN, I think just StyleGAN, maybe StyleGAN 2. I think they may have updated it. But the thing with StyleGAN that it does is it basically updates the GAN architecture. It's a pure like architecture paper, right? And the way it does it is it has this synthesis network that basically does this whole upsampling, but instead of generating from some random noise, it generates from a constant 4x4x512 thing, right? It's just this like tensor that it learns and just says, this is where I start generating from. And it's going to depend on like where your data distribution is, right? And the way it actually injects noise and it injects variation is via this mapping network here. So this is what like a normal GAN is. It's just noise, do a bunch of upsampling and upwards convolution and whatnot, and just get to an image. It instead has a separate network, which is a crap ton of, fully connected layers. And what you're able to do is basically say, you give it a latent, it does this huge transformation to latent to get to some W space that is no longer in the noise distribution, that is no longer in the Gaussian distribution, some other distribution. And you're kind of injecting this noise into every single level of the image. And what people found is that this has two benefits. The first thing is, because you're doing this kind of noise injection thing, it basically performs better. They also scaled it up. The network's pretty big. Very small by today's standards, but it's pretty big at the time. And the important thing is the W space is much more disentangled and editable than the Z space. So what people found back in the days with like the normal GANs is that if you were to do the same thing as VAEs, where like you take two like starting noises and you were to interpolate between them, what will happen is that, yes, you'll kind of get this like smooth morphing between one space to another. However, what this W space allowed us to do is basically say we have an image of a person, say it's just my face, and you have another image of me that's nearly identical, but I have glasses on, right? If we were to interpolate between that in the Z space, then it will eventually interpolate from me not having glasses to me having glasses, but in the middle, I may start smiling and then stop smiling. AKA the features are not disentangled. However, what this mapping network allows us to do, because this is directly fed into all of these, is that this W space here is disentangled. So when I do interpolation instead within this W space, just linearly, or like usually I think they do like a arc sort of thing to keep the magnitude the same, you actually have disentangled features. So it will actually, like, glasses will like very slowly appear in front of my eyes. Or like, like more traditionally, you would be something like a picture of me not smiling and a picture of me smiling, and I'll like slowly start smiling, So that's what's really amazing about style GANs, and GANs are still used a lot today. But the issue is, and also we had like this thing called autoregressive models, which people were experimenting with. It's basically like LSTMs, but let's do it spatially. So like we start with the top left-hand pixel. What are the next 2 pixels based on this? What are the next 3 pixels based on this? It was very janky. It like almost worked, but you can see how it's really slow because it has to like really slowly regressively generate the entire image, and like people just didn't really take it very, very far. But what you've seen here is basically mostly seeing very unstable and jank. Like, these and regressive models never caught on. Like, they did catch on, but like, they were never scaled up to be anything that went beyond the ML circle, right? And GANs, however, were and still are amazing. Goodfellow, who was the person behind, GANs, and who here is in like the CyberX AI collab thing? Yeah, so we have Leon, right? He is also the person who, wrote the, FGSM paper, by the way. That's correct. But yeah, Goodfellow, adversarial AI, incredible papers. The models were very dataset dependent, which means like the dataset itself cannot be very diverse. And the most people have managed to do with GANs, around like 2018 and stuff like that was ImageNet. So like basically you have 1,000 classes, but it was like class condition, you were still very limited. And the question around this time people were asking is, how do we go big? And this remained unanswered for a little bit. Like Big GAN came out 2018, showed that, hey, you can scale up GANs a lot and still be okay with it and actually mitigate a lot of the training data collapse, mode collapse, and a lot of problems that came with GAN training. But people kind of stopped there and went on to other fun, hot things at the time, like transformers, right? That came out in 2017. So this is where diffusion models came in. So let's talk about how that made everything possible. So this is one of the first diffusion papers. The very first one actually came out in 2019, which is Yang Song's score matching model. But that paper is, it's one of the first, but it's much harder to understand than this one, in my opinion. So we're going to start with this one. So the denoising diffusion probabilistic model, or DDPM, is a denoiser that is so good, it generates image from pure noise, as I was talking about, right? Currently, we're not dealing with text right now. We're just trying to generate, we're just trying to generate images of a type of data. Like, for example, in this case, faces, right? And the key is, we're basically showing the model how we go from noise to image by iteratively adding noise. And we're asking, specifically, at x of t, what is the noise that I added from x of t minus 1 to x of t? What is that noise? If I can figure out that noise, then I can go from x of t back to x of t minus 1. And that's what the model is trained on. And specifically, it is conditioned on t, 0 to t, aka like in this case, meaning the model also gets information of how much noise is currently in the image. And to kind of, and as you can see, the generative samples were actually pretty good. This was like starting to rival GANs at the time, which was unheard of until then, because people did not think there was another thing that was going to beat GANs, right? So to further ground this, I want to take a look at the training loop of the diffusion model. Specifically, this is what we do. First, we choose a random image from the data set. Good, right? And then we choose a random t. So like our noise level, say from 1 to 1000, we just choose some random integer in the middle. And we have this noise schedule, A0 to A of 1000, that basically starts at 1, goes all the way to 0. It kind of tells us how much of the original image is there. And it's like a scheduling that's usually like a little bit exponential looking. It's a bunch of math paper that argues for it. But the point is we have this scheduling that goes from 0 to 1 that kind of choose how much we mix the image and noise together, or how much noise we add to the image. And then we sample some Gaussian noise to be added to our initially sampled image. Then we do the following. First thing, we add the noise to the image based on the noise schedule. Can you guys see this actually? Or do you want to move the door? I'll move it a little bit. Yeah. So the first thing we want to do is we want to add the noise to the image based on some sort of noise schedule, right? So in this case, you can see we're basically taking a linear combination of X, our input image, and the noise, right? So and we have the scheduling that determines how we mix them together. That's the first part. So we have a noised image right now. The second part, the model, epsilon theta, and whenever you see in papers, theta, that usually means it's a trainable model. Our model, given the amount of noise t, so it's being told how much noise we're adding, predicts the noise that was added to X. That's very important. We're not predicting the image directly. We're predicting the noise, and there's an explanation for that I'll get into. But we're predicting the noise that was added to X, right? And afterwards, what we do is then we minimize the error between our predicted noise and the actual added noise. So to recap, what the diffusion model is doing, it's basically saying, okay, I have this image that has had noise added to it. What is the noise that I added to the image? So in a way, it's basically trying to separate the noise and the image, just predicting the noise part, right? Does this make sense so far? Yes.
How does the model use t?
So the model use t, we'll talk about that later. Let's talk about that. Hold your horses. But yeah. So to do inference, aka how do we actually generate an image, this is what we do. We start with a Gaussian noise xt, so pure noise, x of 1000 in the case of the DDPM. Then a time step t with image xt. We first predict the noise in xt. We figure out what noise we added to that xt, right? So that's this part. Then we subtract that predicted noise from xt to get what our prediction of the denoised image would be. So that's this part, predicted x0. And then we add slightly less predicted noise back, so we get the predicted x of t minus 1. So to recap, what's basically happening is we're saying we have this model that has a bit of some noise in it, and we have this time step. We figure out what noise that was added to the model, we subtract it to get a clean version of the image, and we're adding a similar amount, that noise that we just subtracted, back, but slightly less, so that we're at effectively x of t minus 1. And the reason why we do this like, we just got rid of the noise while we're adding it back, is because, as you can imagine, at x of like really, really big t's, this prediction of predicted x0 is absolutely horrendous, right? Because it's pure noise, like it doesn't have a really good prediction. But what we're basically doing is we're giving the model a lot of chances to kind of correct itself. So if we give it then another image that's slightly less noise, aka a smaller t, it will have a better prediction. And that's the way diffusion models generate images, is by this kind of regressive process where it's able to self-correct almost. And one more thing is, what you may have noticed, why are we going from x of t to x of t minus 1? If we have 1000 times that, we have to pass through the model 1000 times. That's very, very inefficient, right? And we have the freedom of controlling how much noise we add back into x. So why not do instead just like delta t, right? So the predominant thing right now is we usually train a model with like say 1000 time steps of noise. And then usually when we're predicting, we only do 50 steps of inference. So we're almost jumping a delta t of 20 every single time. So that's the kind of predominant way we're doing sampling really. And you can kind of see how we can skip time steps, maybe at the cost of quality. But what people have found is basically it's not that distinguishable from like 1000 to 50. And like you only start to notice quality degradations around 20 and below. And this process is called DDIM sampling, because the original DDPM paper did not do this. It says you got to do xt minus 1. DDIM basically said, hey, you don't actually have to do that. And also, what the fuck is this? Why do you have this random noise here? What is this term? So this gets very complicated really fast because it goes into a lot of probability theory stuff. But basically, as an aside, there's this term called stochasticity and injecting random noise. The original DDPM paper, the way they formulated it is we're adding noise iteratively from x to x of t. So we're actually going from x0 to x1 to x2 to x3, and we're adding different Gaussian noise every time. But what they recognize is that that's very inefficient, and because it's Gaussian noise, we can reparameterize that whole noise adding process into just one whole noise adding thing. However, the issue is when we're predicting the noise, the noise we predict takes us directly back to x0, but we don't want that. They didn't want that for some reason, but we don't want that. So basically they figured out that adding in a bunch of noise is mathematically equivalent to if we were to do that iterative noise adding process. So, and the DDIM basically said that's stupid, don't do that. So that's what this, random noise idea is. And this random noise idea actually comes back in the next formulation of, in the next formulation of diffusion models, which is the idea that is actually, well, first of all, Yang Song, in 2020, November 2020, actually just said, hey, diffusion models are just SDE solvers. So the idea is that he formulated the diffusion model process as a stochastic differential equation that maps from our easily sampleable noise distribution back to our data distribution that's very difficult to sample, right? And he basically said, hey, we can write it in terms of a stochastic differential equation, and we have an exact solution for how to solve that stochastic differential equation iteratively from this random paper in 1982, right? So he said, yeah, and it worked pretty well, right? However, in June of 2022, Carlos et al. Published this paper that basically said, hey, what we're actually dealing with, like all these formalisms, it's actually just a probability flow ODE, or like put simply, it's just an ordinary differential equation, which means and what our diffusion model is doing, remember, our diffusion model is predicting the noise. What is the noise exactly? It is the thing that took us from data to our noise distribution, right? AKA what we added in the middle, AKA the delta or the gradients from this distribution to this distribution, right? So it is actually a delta. In other words, what our diffusion models are actually outputting is just the delta that we need to go from our noise distribution to our data. It is solving this differential equation. It's just giving us that delta, and we can use any solver, any differential equation solver. So who here has taken Math 30BB? Have you heard of like Euler's method and stuff like that? So for like solving differential equations. The DDIM is exactly a Euler solver. That's just what it is. And this paper came out saying, oh, we can also use like second order solvers and stuff like that. And you can, do this thing. But the takeaway that I want you to have is we show the model how to map from data to noise. And the model now learns to map from noise to data. And that is generative modeling. Does that make sense? Any questions before I move on? Yes?
If we add d time steps of noise to an image, then we denoise it by d time steps. Will we always get back the same image?
That, so not always. And that's actually part of the research challenge that we're doing. And we'll talk about this in section 3, actually. So hold your horses on that. The ideal thing is, yes, we do. But the reality is we usually don't. Because this process is discrete and we're, doing a very large step every time. So eventually if we add some amount of noise and we were to say try to denoise it again, it's any sort of small deviation from the original way that we're adding noise is going to deviate away, and we're going to generate some other image instead. And also units. So units is actually the architecture that's actually behind diffusion models. And this is where, Pratik asked, how do you put in T? It's just, you have, so basically it's units. What units are is kind of like autoencoders. You have some like input image, you kind of try to compress it down, and you try to reconstruct it back. Originally, they used it for like, medical image, like segmentation, and like this absolutely destroyed anything that was there at the time. You have these long skip connections kind of pass data through. And this is what the diffusion model architecture looks like, except they were extra, so they added self-attention layers. Everyone remember attention? Transformers? Pretty good? Yeah. They added self-attention layers to basically try to enforce image coherence. In fact, Percy and I, we have trained diffusion models before. Once he trained a diffusion model for getting to add self-attention layers, and what happened was he was training it on like images like cars, right? And what happened is because the model was not able to kind of look at the image in a global way with the self-attention, they basically started generating headlamps like every single random place in the image. So like what self-attention is able to do is enforce this sort of global coherence, even at these like higher resolution levels. And the sinusoidal T is just kind of like, if you remember like how they did in Transformers, where like they made a sinusoidal and just like added it to like all the layers. It's the same thing here. It's very jank, but basically the model eventually learns that's how, it's able to read time t. So with that out of the way, we can now finally get to part 0, text-to-image models. Hey, look, I can generate anything now. So to do so, we have to first talk about what conditioning is, right? So far, we have looked at unconditional models. So, we cannot control what the model's output distribution is. The only way we can control that distribution is what data we actually feed it during training. So conditioning means we're telling the model more information about the image to guide it, right? And doing so actually improves generation quality and range because the model has a bit more help in what it can generate. Right? So in this case, you want to store your guide in some embeddings, like, class embedding, which you would use sinusoidal embeddings again. Or like depth maps, we can, use like CNN to like compress it down. Or we can do text embeddings with, all the LLMs and, like text encoders that we have talked about before. Again, this is not a new idea. This has been done extensively on a lot of generative modeling paradigms in the past, even beyond CV. But, the very first type of condition that we had sort of is something called class conditioning, which is the idea of like, hey, I have a data set, say ImageNet, I have 1,000 classes. Why not tell the model which class I want to generate? Like during training, tell the model, here, hey, this is the class that this specific image belongs to. So when the model is generating, because it has that class information, it kind of knows what noise to generate, if that makes any sense. So, it helps a little bit. And, like diffusion models begins on image synthesis. This paper, from, I think, OpenAI, basically, did diffusion models, but then they trained it on class conditions. But, Sun et al., hey, it's Yang Song again. In that same paper, proposed something called classifier guidance. So instead of having to train the model with some sort of class information we basically do loss.backward, during inference from a classifier. And this is how it works. First, we, generate an image and the image is like half noisy, right? We pass it into an image classifier to predict, is it panda? And then what we want to do is, because we want the output image to be a panda, we backprop all the way to this original noise that we passed in, or original slightly noisy image that we passed in, to maximize that is panda, right? The very specific output that says is panda. And after we get that gradient, we apply that gradient directly to the next input x of t minus 1. So, in short, what this is saying is, this gradient tells us, where can I further push this noise? Where can I further push this image? So that it goes towards the direction, towards the distribution of pandas. So, because we're doing that pushing, we just apply it to the image again. And we can then start pushing the image towards the distribution of pandas. This is two problems, right? The first one is the classifier must be noisy. It must be able to handle noisy images to be able to say, hey, that's a panda. The second thing is, what you're basically doing is an adversarial attack on the image classifier itself, so you may get really jank results. This is where classifier-free diffusion guidance comes in. And the idea is we're controlling the amount of guidance with 2 diffusion inferences. So when training, we train sometimes with condition and sometimes without conditions. So sometimes we tell the model what class the image belongs to. Sometimes we don't tell the model what class the image belongs to. So we have a separate token that's like the null token, if you will. And basically what we do is 3 steps, right? The first step, we predict like at every single denoising step, we predict what the noise is given our class information or given our prompts, whatever. Then we predict without that condition. We do an unconditional prediction. And basically what we're saying is we're pushing the model in the direction of the condition and pushing it simultaneously away from the direction of no condition. Because we're adding, this is saying this is the direction we go to if we want the output image to be fitting that condition. Say, I want to generate images of huskies. I think that's a husky, right? I don't know dogs. But, we want to generate images of huskies. And this subtraction is saying we want to push it away from generating images that we don't really know the class to. So by doing so, we have this parameter, and usually, nowadays for Stable Diffusion, we set it to like 7, 15, somewhere around that range. But we have this parameter that we can use to control how strongly we want the output image to be part of that class. So it becomes a trade-off of, image generation diversity to how strongly it fits the, class, the actual condition. And usually that means higher quality images as well. So we have this controllable parameter, and that becomes important a little bit later. So we have a way to control condition. And remember, the C doesn't just have to be class information. It can be also text prompts and stuff like that as well. Then we get into text conditioning. How in the world do we actually encode texts? The problem is if you were to just try to encode text prompts with normal large language models, traditional text embeddings don't exactly work that well because they don't contain quote unquote visual information, right? It's trained entirely on text. Why would we expect this text semantic information to be able to work with an image classification model or image generation model? And the way to solve this was a paper from OpenAI called CLIP, which uses contrastive learning. Specifically, say we have a bunch of pairs of text and images, right? So we have this, like a bunch of images labeled with captions. Then what we say is we have two models, an image encoder and a text encoder. And we just pass our data set of text and images through it. And the output of them is just like embedding, say like 128 dimensional vectors, right? You're not actually doing any classification. So it kind of just stops and you have this embedding. And here's what you say. And I think the dimensions usually around 768 to 1024, that's usually the amount we're looking at. If, for any single pair of embeddings, if the original pair were actually a pair of image and text, I want these output embeddings to be the same. If they are not from the same image and text pair dataset, I want them to be different. And that's called contrastive learning, right? It's a part of way to do unsupervised learning if you want to like learn some like embeddings or distribution of a dataset. And because we're doing this, what we're essentially enforcing is because if we pass in a certain text prompt, like, Pepper the Aussie pup, right? The embedding comes out must be the same as what its corresponding image would be through the image encoder. So the embedding must necessarily contain both text and image information. And that's how we were able to do text conditioning for diffusion models. So, yes.
Can we just invert the decoder and then just like skip the whole diffusion process and convert the embedding directly to an image?
You can. Well, you can't really invert a decoder per se, but actually one of the things that people have done, like when I was in DSU, like someone did this, which is basically what you can do is you say, I want to say generate images of Pepper the Aussie pup. And, I get an embedding and I basically say, you basically like start with noise or something. You try to optimize and say, what is the image that would have generated this embedding? It works not very well. Like the images look kind of like grayish and like, if you remember like Google's Deep Dream, where it's like, it's just kind of strange looking, but you can. And it kind of works actually. Like, there are some, I don't think they're good enough to be considered full papers, but, there are, like some random blog posts on the internet that explore this. You can. It's just not very good. Okay. So the problem is we have text conditioning now. How do we actually scale up, the resolution of our diffusion models without going kaboom? Part 0.3. OpenAI with the DALL-E 2 and Google with Imagen. So DALL-E 2 was one of the first text image model that really went viral. So it is what propelled everything into the spotlight and kind of coined the word AI art for real. And it basically did exactly what we said. It projected and add clip embeddings to existing time embeddings. So it kind of used the same way to inject these embeddings at a resolution of 1024 by 1024. I call it the GPU-go-burr method because they had a sort of encoder thing. The paper was not very clear. It was basically a scaled-up version of the Glide paper from December of 2021 in this tiny footnote over here. You can take a look at it. It's like this, but transformer embeds with clip guidance was the whole thing. And then this is also like a sequel to DALL-E. Yeah, the original DALL-E, which is just, they use VQVAs with normal text conditioning methods. But and this is the idea, right? Like this came out, it was really good. It wasn't open source, so some people got API access, r/AI arts had some images posted to it. People saw that this was possible. This was April, right? 2022. And the Google in May immediately followed it up with Imagen. Imagen is a little bit smarter. It performs slightly better than DALL-E 2, and it has lower FID. And what FID is basically, it measures how different two distributions are. So basically what we're trying to measure when we say FID is we have this image distribution, actual data, and the distribution of all images generated by the model. We pass it through some really large vision model to get a bunch of embeddings, visual embeddings of them. And we say how similar are these two distributions? If they're very similar, our model is able to successfully generate images that fit the data distribution, aka we have had a good model. So lower FID, good, right? And it uses T5XSL instead of CLIP. So maybe normal large language models does work. But basically, the way they work is first they train a 64 by 64 diffusion model that is text conditioned, right? So it is able to basically generate like DALL-E, but just at a very small resolution. And then they train two separate super resolution models. One going from 64 to 64 to 256, one going from 256 to 1024. And specifically, this super resolution model is text conditions. So it knows how to do super resolution, but it also has the information of how it's supposed to up-res it. Right? So because we have this two-stage training, it was, first of all, more efficient to train, I think. It's around the same size as all the other models. I think DALL-E 2 was twice the size of this. But it's much more efficient to get to 1024 by 1024 because it has a multi-stage solution. And also it has a multi-res option because like if you were to do, say, random stuff to like do optimization stuff, all of these are images and can do everything at every single one of these levels. So it becomes really fun to mess around with as well. But again, it is not open sourced, right? There's a lot of papers that came out of Google research that, used this in-house model, but then, we plebeians could never actually access it. So this is where latent diffusion models came along. They had a slightly different idea to how we were to kind of scale images up from small resolution to large resolution. This paper, the latent diffusion models, first came out in December 2021 from the LMU Munich University. It's a lab called CompVis. That lab becomes very, very important in a little bit, so keep that in mind. But basically, what they're doing is first they train an autoencoder. Remember what autoencoders are? Image, latent space, back to image. We're compressing an image, right? So let's say we have like 512 images. We're trying to compress it down to a much smaller resolution, like 64 by 64, right? We first just train an autoencoder to do exactly that. I have this large, high-resolution image, compress it down, and then have some way of being able to inflate it back using a decoder. So we have this first-stage autoencoder, and we freeze it. We don't touch it anymore. Then what we do is, inside our latent space, we have a distribution that is a little bit difficult to do, but it's a much smaller resolution. And we just train a diffusion model on that distribution instead, the latent distribution instead. So then the model pipeline becomes this. For generation, we start with some 64 by 64 Gaussian noise. We do this whole denoising through generator. And the reason why I invert this image is to say, this is not the final image. This is the image within the latent space. So it's going to look like a little bit wonky and with weird colors and stuff like that. We denoise it. We get a latent result. And obviously when we're denoising, we, put in our text, right? And then we use a decoder to inflate it back to 512 and 512. And that's how latent diffusion models work and how we're able to get to higher resolutions relatively efficiently. Yes, Pratik?
Shouldn't the noise sampled inside the latent space already map to like a reasonable image?
No, because the thing is, if you remember, with autoencoders, you're compressing it down, but there's no limitation whatsoever what the intermediate distribution is, what our latent distribution is. In fact, I didn't include this visuals for this because it was literally made finishing off the last slide like 5 minutes before it started. But what you will see is actually the image that gets encoded is actually sort of kind of looks like what the output image will be.
Yeah, that's what I meant. So you could hypothetically just train the autoencoder really well and you don't need the diffusion process. Well, then it just becomes a normal autoencoder, right? And then suddenly we have all the problems with autoencoders, which is bad to scale up. It's blurry and we don't have all these kind of robust, properties of the diffusion model. So you can, but it just becomes another autoencoder and you're back to VQVAEs. And it's like, what's the point? So, and people show that VQVAEs don't really work well. So they're basically just using an autoencoder as a way to compress images down. Generate images in this compressed space, inflate it back with a decoder, right? So LDMs, or latent diffusion models, is the framework that make stable diffusion. Hey, we know that. That's what we're here for, right? Woo! We got it. Pretty good. Basically, stable diffusion was when Stability AI at the time went to LLM Munich and said, hey, that's interesting. Let's work with you to train a basically much better version of this. They trained on Lion 5V, which is 5 billion text data images that just completely scraped from the internet. You can see how that becomes problematic very, very quickly. They have an open source, not open source, they have a free version of it now, which is like that, but no copyright images are in it, which is equally problematic. But at least they won't get sued. And the most important thing is it's open source, right? They put the weights out and people could do a lot of research with it. Also, shout out to Hugging Face diffusers for basically making ML code actually readable, and they integrated a lot of these into things that you can actually run, and it makes research a lot easier because if there's one thing that most ML scientists can't do is write good code. So they can do great research, but their code, absolutely not. But yeah, so and all this uses also classifier guidance for text conditioning as well, so we can control how strongly the text condition is on the image. And one thing is, if you just keep pushing the classifier guidance up, what actually happens is the image becomes really contrasty, it's very much this class, but then you take a hit on image quality again. So that's why we have classifier guidance value of around 7 to 15 usually at the end. Does all this make sense so far? So we're at stable diffusion now. Yes.
So you want to do it with a smaller image because it's just easier to train.
It's much easier to train, much smaller model number parameters, and most importantly, if it's smaller, the model has it doesn't have to worry about trying to upscale nearly as much, and it can be more expressive, basically. And some people argue that the advantage of doing this kind of generation within a latent space versus what Imagen is doing, which is basically a smaller resolution version of the image, is that the latent space is more expressive because you can take advantage of all the idiosyncrasies of your autoencoder to try to generate good looking images.
Oh yeah, that's my next question. How do we know that the latent space is like actually latent? So the latent space just means that or just like if you change like something, it'll like change like smoothly. How do we like know? Is that like something that's like tied to the model itself?
It is tied to the autoencoder.
Or is it just something like?
It is tied to the autoencoder. The autoencoder, like what people have found is that autoencoders generally have like smooth latent spaces.
Do they just find that they're like testing it, or is there something like in the math?
I think there probably is something in the math, but because technically autoencoders you can just formulate it as like PCA, right? Like principal component analysis, and like that's smooth. It's just like that, but non-linear. So people were like, yeah, it's probably linear. Again, like a lot of ML is not math backed, but like people basically found that autoencoders are usually smooth enough and it's fine.
Because the loss function forces the latent space to be normal.
That's not autoencoders. That's variational autoencoders.
That's not in there in autoencoders?
This I think is just a normal autoencoder. I don't know if it's a variational one. I don't think it's a variational one. This is just a normal autoencoder. Yeah, because variational ones are for generation, but we're not generating with this autoencoder. We're just trying to compress the image space to latent space. Yes.
So what if you want your ending image to be a rectangle, not a square?
Oh, so we realize these image generators, it's UNets, right? It's just a bunch of convolutions. The great thing about convolutions is it doesn't have a limit on where your input size is, right? And even it's intermediate layers in the middle, they're all attention, which means because what we're basically doing is taking the image and basically putting it into like tokens of sequences. They're basically a sequence of things, so like there's no limits on how big that can be as well. So basically all we have to do is, we can, if you want to say make this like wider, you can do like 128 by 64, and you have a wider noise. It generates a wider thing, and when you go through a decoder, which is all just CNNs, it just generates a wider image. And that's how people have been able to generate really, really high resolution images from diffusion models, is just like literally making this thing bigger. But you can see some issues where it's like, oh, but like, all the kernels learn to generate, objects at like this certain resolution. So like, if you go bigger, all the objects are a little bit small. It feels like a wider angle image almost, right? Because that's what the models is trained to do. Later, iterations of Stable Diffusion and other generative models try to mitigate this by adding extra conditions on like resolution, stuff like that. But like one of the things that, actually according to one of the co-authors of Stable Video Diffusion is they found that these models typically really bad at generating. So if you start at 32 by 32 and you try to generate an image, the quality becomes awful, but it's actually really easy to just fine-tune a model on higher resolutions and get really good results. So that's just something to keep in mind. But does that kind of answer your question? Yeah. Okay, cool. All right, so now we're all caught up, right? Like this is all the papers that we have, so far talked about, right? August of 2022. We're, that's like, a year and something else from today. Like how much did people do around that time? Okay. Yeah. Part 1, controllable generation. So, this is where this presentation is supposed to actually start. And let's actually get started. Now you have an idea of what text-to-image models are. So, first of all, what is controllable generation? The question is basically, can we condition text-to-image models beyond the text form? It's like, yes, we can. The idea is that diffusion models are a powerful base generator, and we have to somehow inject additional information into it, like depth maps. Can we make a certain word more prominent? Can we inject the identity of a certain thing? So I'm going to start with the first part, which is training free image editing. AKA, we're not training anything else. We're just kind of manipulating things that's within the diffusion model. And attention is literally all you need. Because what the prompt-to-prompt paper found out, this is actually on Imagen, not on Stable Diffusion because it's a Google paper, is you can manipulate the cross-tension layers of diffusion models by literally just like making it more. Like you just fucking scale this up. And what you're essentially able to do is basically say, the boulevards are crowded today. You can just take the attention map for crowded, literally scale it down, and the result becomes the image but less crowded. And you can do a lot of things. Like for example, I can photo of a cat riding on a bicycle. You can make a photo of a cat riding a cat and riding a car. And the way you would do it is basically just take the attention of car and just replace the attention intermediate layers every single iteration. Same with, like adding extra styles and like, you can do all these things just by screwing around with the intermediate attention layers.
Just changing the key matrix?
Basically. Key and value, usually. You keep the query the same, key and value. So, you can kind of see here, let's like, again, just to kind of refresh on where the attention came from. So a layer in Stable Diffusion usually looks like this. You have some resonant layer, right? You have like two convolutions with a skip, right? You have this resonant layer. Then you reshape this layer into like patches or tokens. And you first pass that through self-attention. And this self-attention is very important because, as I said, and enforces self-coherence, right? So even if you like mess up the cross-attention, some weird manipulation thing in the middle, because you're doing this every single step iteratively, if you do something that causes it to have an artifact, to have a weird looking image, when you pass it back into the model again, the model self-attention will go, wait, that looks weird. I'm going to correct that. So the self-attention is very, very important. And then we have cross-attention, which is where we actually put in our text encoder, right? The output token is our text encoder. And because there's attention, it's basically, we have this corresponding between the intermediate layers with every single word in the thing. So we can say, I want to take astronaut and say, make it bigger. Or say, take astronaut, just remove it or stuff like that. Because we have each of these tokens corresponding to each of these texts. So specifically, self-attention, the QKV are all from the resin layer output, right? Remember, QKV comes from actual just linear projections. You have 3 linear projections. It gets you to that. So QKV are all from the resin layer outputs. Whereas with cross-attention, Q, our query, is from our ResNet, and K and E are from the text encoder. Does that make sense? Yeah. So that's basically what prompt-to-font said. Is hey, we can just mess around with the attention layers, and it's fine. It's fine. And my fluffy bunny doll, you can make it fluffy, literally. And you can add jelly beans to it by just injecting extra attention layers. It's kind of crazy when this first came out, you can kind of see. It's people didn't realize, people knew diffusion models were robust. They didn't know that it was this robust. Yes, Pratik?
Is there a practical difference between messing with the attention layer and the stage in the prompt?
So this actually gets us to the, yes. In short, yes. Because what you can do is, for example, if you were to just change the prompt, you would be generating a completely different image, right? But you want to keep everything else the same, but just edit that part. And this may not be very helpful if it's just your reference image here is just an image you generated. But what if your reference image were real image, right? But then the problem becomes, how do you generate a real image? We have this real image, and our goal is to figure out what is the text prompt and noise that would generate this image, right? Because that's the way for us to basically make the diffusion model regenerate the image, but we do all these manipulations to actually edit the image itself. And there's 2 ways to do this. The first way is something called DDIM inversion, which is basically saying it's just DDIM, but instead of subtracting noise, we're adding noise every single time. And it makes the assumption that the noise from from 2 time steps, from x of t plus 1 to x of t should be close enough to the noise from x of t to x of t minus 1 that because when we put in x of t, it tells us how to get from x of t to x of t minus 1, right? But we're adding it to the x of t to get to x of t plus 1. So there's this assumption that we're making. So this is not a perfect way to do inversion, but it's good enough for a lot of purposes. However, the same authors from Prompt to Prompt also released a paper around the same time called no text inversion, which basically optimizes the no text token for classifier view guidance. Remember, for classifier view guidance, we have a no text that basically says we want to push the model away from not generating images that are unclear which class or prompt it belongs to. So basically what we're doing is we're optimizing this no text token to not just push the model away from not being any class, but we're actually pushing the model away from not looking like the target image that we want, or not looking like the real image that we want. So we do this for every single time step, and we're able to do inversion really, really well, as you can see here, right? We have this input cat picture. I've stared at this picture so many times. Because this is one of the example images from Prompt to Prompt, and I just keep using this one to make sure my own things work. But if you can invert this picture of a cat standing next to a mirror. This is for if you were to do DDIM inversion. You can see it looks quite different, right? But looks very close. If you were to actually zoom in, if you have this presentation pulled up or something, you'll be able to see some details are not exactly the same, but the global features are very similar, right? And what you can do is actually just start replacing prompts if you want, and it will start editing the image. And you can use other prompt to prompt techniques to do very subtle adjustments. So yes, you can, but you have to do inversion first to keep the image the same. To answer your question, does that make sense?
Yeah.
Any questions before I move on? Okay. Then we have this paper called Plug and Play from November 2022. Basically what it does is even simpler. Inject self-attention features for the first few time steps from real input image. So generated images share the visual features. That's it. All it says is, if I have an image, this input real image, and I want to generate images that share the semantic structure, overall structure of that image, just invert this image so you're able to then pass it through the diffusion model and basically figure out what its KVs are for every single one of the intermediate layers. Replace during generation. That's all it says. Again, attention is literally all you need. And you're able to basically try to be able to preserve the overall structure of the image pretty well and almost basically achieve this sort of image editing, but in this case, they frame it as plug and play. Like you have these features that you can use to plug into diffusion models. This KVs can just replace out, and you'll be able to generate images with those exact same structures. Does that make sense? So that's plug and play. And then we have another one, which is zero-shot image to image translation, or pix-to-pix zero. This one's a little bit different. It does this, but on the text prompt directly. So the idea is this. Let's say I want to figure out some edit direction on the text prompt to go from cat to dog very reliably. If you were to say just like do the whole like null text inversion thing, what happens is the image looks similar, but say the dog may look like that, right? It's like it looks a little bit too different. What if I want them to look much more similar? And the key is to just touch the text prompt, don't touch anything else. The idea is this. We first say we want to go from cat to dog. We ask GPT-3 to generate 1,000 sentences containing the word cat. We ask GPT-3 to generate 1,000 sentences containing the word dog. We get embeddings for both of them and figure out the mean difference between them. So we're going essentially from the text space of cat to the text space dog, and we just basically add this edit direction to the image. It works. Again, the crazy thing about diffusion models, you can do all these jank training-free things, and it bloody works. Like, it's insane. And because, again, it's so robust, and because you have this, like, time step, you're passing the image back to itself, any artifact that happens will get self-corrected by the model, or will get largely self-corrected by the model. That's why diffusion models are so powerful. That's why we need this iterative process. A lot of these training-free methods, like nowadays people are doing, like, one-step diffusion. Don't work on those, because there's no self-correction in there, right? Well, at least from my, like, very brief testing, they are very jank on those. But, like, this is why the diffusion model formulation is so important. Because we can do crap like this, right? Okay. And later, people realize you don't even, like, you can also just do, like, basically grounding generations. Like, I want this thing to be in this location. And the colors are, they also inject color information. But basically, this one's directly mask and manipulate the self-attention and cross-attention features to limit specific concepts to input regions. What we're basically doing is we're saying, we have this self-attention layer, right? This is, for the word yellow. It currently looks like this weird thing. Masked so it only appears in the part that we want it to be. That's it. That's it. And same with, say we have like the word, dress, right? It's currently around here. So this is when the model should generate an image. I want it to be down here, so mask it so it only appears here. That's all you're doing. And it works. Because, again, the self-correction property of the diffusion model. It's pretty cool, huh? So this is a paper from CMU. And this is where we move on to, but what if we can train, right? We have GPUs, right? We can train things. Those LLM peoples, they can give us like a cluster. That's good enough. So this is where ControlNet came along. This paper really, really went famous because people realized they can take real life images and make people do things, which is very bad. But the idea is that we're able to add any visual, this is very important, visual condition to pre-trained diffusion models, such as edge maps, depth maps, stuff like that, right? Do I have another visual here? No, I don't. But yeah, like this is the idea. If you click on the actual demo itself, you will see that they have like a crap ton of examples and a bunch of like models trained. Like you can do like, edge canny maps. You can do like HD lines. You can do like this thing. You can do scribbles. You can do all this stuff, right? Like there's a lot. They've trained a lot of different versions for this. And basically, the way this works is they basically said, okay, we have this diffusion model, and the first part of it is our encoder, right? Because it's a unit. We have an encoder, we have a decoder. This has nothing to do with the V8, the autoencoder out front. This is just a diffusion model itself. We take the first half. This first half must be a really good image encoder because it is able to basically encode our input like noised image and be able to then inflate it again to generate us to predict the noise. So this must capture a lot of information about any sort of input image. So let's take this. Well, let's freeze the model, take the encoder part, duplicate the thing, and basically use this as our input for our condition. So any depth map, edge map, or even pose information. Because these all like visually look like what the final image is going to be, this encoder is able to extract information. And we basically only train this encoder to be able to inject this information to our decoder. That's how ControlNet works. And specifically, they do one more thing that is pretty clever, which is they have this extra zero convolution above every single one of these layers. And the key to doing this is zero convolution is basically a convolution, but you initialize with all zeros. It's because initially, when you initialize them with all zeros, you're just adding 0 to every single one of these layers, right? Which means you're not modifying the model itself. So, and as you train it, these zero convolutions will slowly gradient descend to have values. So instead of the moment we start fine-tuning the model for the model to break, it slowly introduces this conditioning idea, eventually injecting it into the model. Does that make sense? Yes.
Does that actually make a difference though? Shouldn't it convert?
It makes a huge difference. Actually, let me show you what it looks like in the original paper, because the original paper has a pretty good illustration of why a pretty interesting effect from this. Here, right? So they basically train it on just this image. So the test input is this. At training step 100, it's just like apples, right? At some step, the zero convolution, like it suddenly learns, oh, this is what I have to do. So from step 6100 to 6133, it snaps and it understands this is how you generate the image. And they observe this over and over again, even for data sets where it's not just this image, right? But like they observe that. And that's very cool. So this zero convolution idea allows them to start training a diffusion model without breaking it, right? With almost like this zero convolution is a way for them to say, I'm controlling how much I'm messing up this model. I'm controlling how much I'm inputting this model. So in the beginning, we're not modifying the model at all, and we're slowly kind of training so it, starts being able to affect the model. And some of you may be thinking, wait, it's zero convolution. Won't that make the gradient 0? They actually did a derivation in the paper that says, no, it's not. It's not 0.
Are you replacing the residual connections between the encoder and decoder with the...
Replacing? What do you mean?
Like normally the encoder and decoder would have like residual connections connecting them, right?
Yeah, like this? No, You're just using this. This is a completely separate module.
Like, I see. So you're just adding those on top of the residual connection.
Yeah, you're basically taking these outputs and literally just like zero convolution, just adding it to the outputs of every single one of these.
I see.
Yeah, that's ControlNet. So there's actually 2 more papers that are kind of like this, but they're a little bit different and I think it's worth talking about. The first one is Imagen, which opens at grounded text to image generation. And it's actually came like a month before diffusion, so like all 3 of these works are concurrent. And basically this work approaches things a little bit differently. Because unlike Stable Diffusion, unlike ControlNet, it can take discrete conditions. For example, bounding boxes and text embeddings. Conditions that don't have an immediate visual correspondence to the model itself. It doesn't have an immediate visual correspondence to the output. Because like, what do you mean by text embedding? Like, if I want to say, I want a specific object in this very specific location, ControlNet can't do that because it can't take text information, right? So, what this model does is it says, okay, we have, if you remember how the Stable Diffusion models work, we have our self-attention, we have our cross-attention. Let's put this additional thing, gated self-attention in there, which is basically this additional like attention block that we train to inject all these like discrete information. And they do the same thing where they do like a zero gating, but like in this case, instead of zero convolution, they just do a output of this multiplied by this gamma variable that's initialized to all zeros. So when they start training the model, it doesn't affect anything. But this gamma eventually becomes, gradient descended and learns to not be 0 anymore, and it slowly introduces this injected information. And they're also able to do things like depth maps and stuff like that, but by basically jointly training like a CNN encoder that encodes to a certain text embedding, that gets injected into this. So it's more flexible. However, the downside is the image quality is not as good as ControlNet and is less robust than ControlNet. Because ControlNet, what they're basically doing is because they're just using convolutions that directly map to what the output's supposed to be, there's a much stronger sort of pixel level correspondence. But with Imagen, because you're doing this in the self-attention section, the correspondence is much weaker, which means though you're able to do more, the effect is usually like, the image quality is usually a little bit worse. And also, this was started out as a Microsoft project and then became a university lab project, so they didn't have as many GPUs to train as well. This, I believe, was UW-Madison, and the other ControlNet was actually from Stanford. Stanford has more GPUs. But yeah, so and another thing they do is they only run Imagen for like the first few steps, because what they realize is the structure of the image is already decided in like the first few steps of denoising. Like I think they only do like the first like 20% or like some really like 30% of the time steps. And afterwards just let the model diffuse on its own. Because they also realize that if you just keep making it run the whole thing, the image quality actually becomes pretty jank. Last thing, T2I adapter. So this one is from Tencent, again, a concurrent work. And it's very similar to Imagen, but specifically, instead of having these like, intermediate attention modules that's like pretty hard to implement because you have to like put it in the model, they have this separate adapter thing that basically does the same level of sort of like attention injection. So it's kind of like a combination of ControlNets and Imagen, where like they have the separate module that's very easily, replaceable, and you can take it out very easily in code. But they specifically do attention level injection. And specifically, what they realize they can do is they can just like stack up a bunch of these adapters for like different purposes and do basically different levels of conditions. So for example, I didn't show it here, but like in the paper they also show that, for example, I can do, let me see if I can just like bring it up. I think that'll be the easiest. You can actually inject use multiple of these adapters, train on different conditions, and basically do like, I have this depth map, but I also want the person sitting on it, and they're able to generate out of it. So you can kind of see how all three of these papers have their own advantages and disadvantages. ControlNet is the one that became the most famous because these are a little bit more specific than the other ones, and the prompts, requires a little bit more engineering. But all of these show how like, hey, you can just inject stuff into diffusion models. We saw that with the training free methods, but we can also train specific things to inject into the diffusion model, right? So does this all make sense so far? Okay. Then guidance is all you need. So there's this paper called Universal Guidance, and basically what they say is you can basically just loss.backward W and just like use like kind of like classifier free guidance but on any loss to make the model generate anything that fits a certain loss. Like for example, you can make the model generate an image of a specific person by minimizing the loss of a facial recognition network. You can make the model do this grounded generation situation by optimizing the loss of a segmentation, like a localization, like Dino and stuff, not Dino, like the bounding box model, right? You can make the model, generate a certain thing with a certain shape by optimizing it with a loss of a segmentation model, right? So any arbitrary loss we can use to guide the model, and the way we do it is, I thought I animated this so it appears one by one, but it doesn't. But like, basically, again, we pass the noisy outputs from into the model. We get this noisy output. We pass that into the guidance model to get some loss, right? And the output is actually not going to be noisy. We're going to use this to predict what the unnoised version is. So it's going to be very janky in the beginning, but it's going to get better as the time goes on. And we get this loss that we're trying to minimize. Backprop it all the way to what this noise direction is, and we just apply the gradients to the next iteration. Again, what we're saying is, according to the law, this loss tells us the direction to push the output distribution so that it will be minimized for whatever loss that we're using. I think this paper actually got rejected from ICLR 2023. Like, these papers are so new, some of them are still in decision whether they're accepted by the conferences. But like, basically, we have very similar issues with like adversarial attacks and stuff like that, but basically they say, hey, we can just use optimization to do a lot of these things.
Oh, wait.
Jackson?
Do you have to do this like at every time step, or can you like start injecting it later on?
So usually if you want to start injecting, you actually want to start earlier. Because what people found is that the global features of an image is often determined in the first few time steps, which is actually very tricky because the output predicted X0 of the first few time steps is also the worst, right? So this is very challenging on its own. So like if you were to only do it for a few time steps, you would do it in the beginning time steps, aka the first few very noisy time steps versus the non-noisy time steps. Pratik.
Optimizing the noise instead of just optimizing the generator seems like it gets worse results.
Oh, like just optimizing generator itself?
With respect to that guidance loss, yeah.
Yeah, the issue with optimizing generator is very expensive. This thing has like 800 million parameters? This is a 64 by 64 by 4 image. Right? And also another thing with optimizing the generator is the way the model is diffusing becomes shifts as you're going on, which is not really something we want because this assumes a certain level of noise, but we don't want this thing to be shifting as we're in the middle of denoising, right? So like we don't want to optimize the generator directly. Does that kind of make sense? What's going on here? Okay, cool. Okay, so there's this paper from Berkeley in June. By the way, this was all happening when I was like in the middle of doing a lot of this research. I was like, oh, this is a lot of these things are happening. The graduate kept just sending me papers. But basically what this is guidance, but a loss function is based on attention features, right? So what we saw before with universal guidance is the guidance, it's based on some output image. And usually what you have to do is actually have to pass the image to like a decoder. And passing it through a decoder is very, very expensive. So what they did is, hey, let's just do it like within the attention features itself. Because the attention features contains like the location information and also the size and the scale information of a lot of these objects. Why don't we just optimize that directly? And that's basically what this paper did, is you're able to then say, we have this original image. perfectly normal image. And then you can like say, oh, I want to swap the location of these two objects. And the way you would do is you basically, all of these have a corresponding like features within the feature space, right? You have this cluster of pixels, you can calculate the centroid of it. And you basically say, I want the centroid to be some other location. That's how you would be able to move it around. And they define a bunch of these losses for like, enlarging things, replacing things, copying scene appearances, and it can all done by optimization. So again, like if you remember, this part is just normal classifier free guidance. We have, generate the image with the guidance, generate the image with a null token. We do our, subtraction thing. We use S instead of omega here because papers. But we additionally add this extra loss, which is our kind of feature guidance to want to push it towards, minimizing stuff, right? So, however, this actually takes a very long time because, their paper, they run it through all 1,000 time steps because self-correction, right? But it takes a while. But then I actually tested it later, you don't actually need all 1,000. I don't know why they did this, but yeah, it's a paper. Oh, actually, the demo of this actually does seem pretty cool as well. I will very quickly show you guys. So, they actually show this, little demo. It's like, oh, okay, we have, this, raccoon, we can move it down, we can move it left, right, shrink it, or make it larger. It's pretty cool. All right. And a lot of these, if you were to edit real images, you can kind of see how you need inversion. This is why I talked about inversion at the very beginning. It's like when we're saying editing real images, you just do an inversion, and then you do all this thing, right? Now, oh, yes.
For this,
yeah.
How similar are the images? Could you, for example, slowly shift stuff around and then just make a movie out of it, like a video?
That is actually, okay. So that's a separate paper. There's a paper called Dragon Fusion. Okay. There was a paper in 2019, 2022 or something called Drag Your GAN, which is basically people did they used, this was back in generative adversarial networks. They optimize the W so that you can slowly drag certain features of things to each other and you make a movie out of it. With this one, you can do a very similar thing with Drag Your Diffusion. Drag Your GAN came out, and 2 months after Drag Your Diffusion came up, because someone's like, I can make a paper out of this. No disrespect, the paper is still pretty cool, but you can do stuff like that. But you can see how Drag Your Diffusion is very annoying to do because every single frame you do all your 50 steps of inference. So, and at that point, you might as well just use, say, Legion, just have a bounding box that moves across the frame. Right? Is that gonna make sense? Yeah. Okay, fine-tuning. So I want to talk about two papers for fine-tuning. The first one is LoRA. So LoRA, which is lowering adaptation of large language models, is actually originally for large language models, as the title suggests. And the way it works is basically in large language models, you have a bunch of just fully connected layers, right? WX plus B, whatever, right? You have all these fully connected layers, but our goal is to basically say, I want to fine-tune this model, but I want to make the fine-tuning that I'm doing, aka almost like the delta theta. So it's kind of like the change in the model weights I'm doing. I want to make it very small because I don't want to make the delta weights to be the same shape as the original one. This is really huge. So what they basically say is, okay, we have this, D times D, really, really big, fully connected layer. Let's approximate it with a matrix that maps it to some really low R. The R goes 1 to 4, so really, really low. And then we just inflate it back. So that's why it's really, really low rank, right? So then the dimensionality of these when multiplied together is the same as this one, but it's kind of an approximation of this. And the idea is that when we're doing fine tuning, we're making such small, adjustments that this is able to capture most of the information. So that's basically what they're doing. And again, see, initialize B with 0. It's like zero gating, right? You start with not breaking the model, and you slowly optimize so that it becomes it becomes not zero, right? So that's the idea. And the amazing thing is you can do this with Stable Diffusion as well. With convolution layers, it becomes a little bit more annoying because you do it for each filter, but it's the same idea, right? Stable Diffusion is usually on 5 gigabytes. A LoRA model can be around 30 megabytes. It's pretty good. That's pretty good. And most of these you actually see on Clip AI. This is all weird. Most of the AI form models come from. B of 0 is kind of similar to zero gating, but the idea is that you have this way to fine tune the model that's very, very lightweight and you can just kind of swap these out, put multiple of these in, whatever you want to do. All right. However, the issue is, what do we want to generate a particular subject? For example, I want to generate this dog specifically, right? And you would say, I want to generate a picture of a dog. It's not going to be this dog. And the problem is, if you were to just fine tune directly, on, say, the set of these 4 images, it causes overfitting, right? So you can kind of see it here. So if you were to fine tune directly on these set of images, it causes overfitting where it actually does decently well placing in different scenarios, but it's the same pose from a dog. So the solution to that is a paper called Dream Booth. And they're called Dream Booth because they say it's like a photo booth. But once the subject is captured, it can be synthesized wherever your dream takes you. But the idea is you're still doing fine-tuning, but you have an additional loss. So first of all, you fine-tune with a unique identifier of V. I think it literally doesn't matter what this unique identifier is. It just has to be a word that no one ever uses. Like, I think one thing that people use a lot is SKS. I have no idea why, but that's what people use. And basically, so instead of fine-tuning with the prompt a photo of a dog, you would fine-tune with the prompt a photo of a V dog or a photo of a dog, right? And however, you have one additional loss, which is the class that you're fine-tuning is dog, right? Then you would, before you even start fine-tuning, you would generate, say, like 400 images of a photo of a dog. So 400 different variations of a photo of a dog. And you're adding a preservation loss to basically say, while I'm fine-tuning this, also make sure that when I just generate a photo of a dog, not a photo of a V dog, right? Just a normal photo of a dog, it stays the same. So it's basically a regularization method for us to say, learn what this V is, learn what the identity of this thing is, but don't change anything else. Don't change the outputs of any other prompt. Does that make sense? And we're able to really, really nicely do Dream Booth like this. I've trained a model with myself in it. It looks horrifying, but it works, right? I'll show you guys later. I don't have the pictures with it right now, but like, it works. And, yeah. So, yeah, this V can be anything, we usually use SKS for me. So that's Dream Booth. That's what a lot of people like. If you see people like images of celebrities, and like usually with like most like higher profile celebrities, the text prompt is enough to, contain their information. But the way that, there was this one startup that said, hey, we can generate like AI, LinkedIn profile pictures for you, right? And then like we raise like $10 million. It's literally just fucking Dream Booth. I don't understand how they raise so much money. It's just this. It's just this packaged, like when you understand how these work behind the scenes and how simple they are to actually implement, like I can train one of these. Like I trained like to make sure my code was working. I trained this on it takes 10 minutes. Like it's really quick. It takes 10 minutes on like a 3090, which is like not very little, but like like on a laptop maybe like at most like 2 hours. Like it's not bad to train at all. Yes.
Is the point of the preservation loss that your model learns what your dog is, but it also doesn't mess up its other results?
Exactly.
But then why would you need that? Because if you want to train something that's not your dog, just go back to the base model.
Because the thing is, it doesn't just learn what your dog is. It learns the specific situation that your dog is in. Like the pose, like in this example, right? The dog is in a very similar pose for every single one of these images. So without this loss, it remains in that position. However, if you make this regularization loss, what the model realizes is basically, the only difference is V here. This V becomes almost like a style token to remember what your dog's identity is. So when you generate images of that dog with a V, you can have it in actually different poses because it takes information from the original dog class.
Sure. And you said it's faster to train, but even though you're using preservation loss, you're still backed up into the whole thing though.
Yeah. When I say faster to train, I mean like relatively fast. Like it doesn't take that many iterations.
Right.
If you're just doing normal fine tuning, it's going to take even faster. Like around like 100, 200 images, you're able to see the effect already. Does that make sense? Okay. Hold on, one second. Okay, so what we have seen so far is a lot of different ways to manipulate the model, right? And a lot of these, with the training-free controls is messing with the attention layers. However, it's not able to do something as complex as what ControlNet is able to do, which is like, have this sort of like really strong pixel level correspondence. And we also see with some of these like, and a lot of these models actually also work with Dream Booth. Like you can apply ControlNet to a Dream Booth and it will work. So the question becomes, can we do all this training free? And the answer is we can actually. This is a very recent paper, literally December, right? Free control. And basically what they do is they say, okay, we first generate a bunch of images of the class that we're trying to generate. Then we calculate the intermediate features, the principal components, all of those intermediate features, to get basically a basis vector. In this case, if you remember what principal component analysis is, or what you're able to do is the first few vectors correspond to the actual like spatial features of the image, right? And the rest are like the details. So we only take like the first 20 or like 30 vectors and just keep that as like our little, like almost like plug and play like features. Then when we're generating an image, as we're generating this image, we can project the intermediate features into these spaces and say, I want the coefficients to match this one. The first 20 coefficients to match this one. And what you're able to do is by optimizing that loss specifically with guidance, you can try to pull the output features of the image closer to our input condition. And because it's completely training free, as long as the image contains any visual information, it is able to extract a very similar on PCA because, this paper, they realized that even with different modalities of the image, when you pass it through a model, there is a very similar sort of correspondence. Like the PCA features actually look very, very similar, right? So by doing so, you're able to generate images completely training free with bundle optimization, like about a minute per image. And you're able to do any sort of input conditions. You don't have to train a separate thing every time. So you basically have ControlNet and image-to-image task, complete training free. And one of the reasons why I wanted to talk about this paper is because, look, that's my name. I didn't do that much on this paper, but it was really fun working with my grad students on this paper, and it's getting released in like 2 days on our archive. So check it out. Okay, so now we have talked a lot about image generation, right? But can we go beyond 2D images? And it's basically going to be a combination of video generation and also some other modalities. First, part 2.1, GPU generation for the GPU-deprived, aka university labs. So the very, very first paper is a paper called Text to Video 0, which basically says, again, attention. It's attention again, right? You're using KMV features from the very first frame. So you basically let's say you generate 16 frames. You generate 16 frames independently. However, you generate the first frame and you use the KV features from the first frame on all subsequent frames. And what they realize is that that actually allows you to maintain pretty good visual consistency. And another thing they realize, and they also do some initial noise thing that makes it so that the initial noise is there's variations, but it kind of matches the thing. And they also do some background smoothing under the end with a bunch of masking stuff. But basically what they realize is, even if you generate these 16 frames completely separately, as long as you play it back at a slow enough frame rate, it looks like a video. So that's why these are really good at generating prompts such as someone waving their hands, because I can have my hand look like this, and if it's played slow enough, it will look like I'm waving my hands. So it's not really a video per se, but they basically found a really good way to ensure sort of this temporal consistency when you generate a bunch of images simultaneously. And when you combine it with ControlNet, say with edge maps taken from an actual video, or images taken from an actual video, or this sort of KV injection can actually get us really, really good results. So that's it works well with condition or pix-to-pix add-ons. This is a separate pix-to-pix model that they have with control with Stable Diffusion. Does this make sense? So again, we're back to just messing around with attention again. Half of these papers are just hey, attention go burr, but it works. It works really well, which is why people keep using it. And then we have this paper. The only reason I want to show this paper is because how atrocious that diagram looks. But I want to show it because this uses ControlNet plus OctoFlow estimator plus warping plus inpainting for really, really smooth video-to-video translation. That's incredible. That's incredible. And the way they do this is basically they start from something like input frame X0. They basically first group the video into separate frames. They're taking inspiration from actual MP4, H.264 compression. And they basically say, we have this input frame. We pass it through ControlNet to get some sort of translation thing. Say we use a depth map, for example. And then using the subsequent frames, we can predict the flow of the image using optical flow estimators and basically shift these pixels to that location. And then if there's any blank spots that results in that, use the Stable Diffusion to inpaint those. And you do this for keyframes. You're able to generate really, really long videos that have really, really good consistency.
How do they identify blank spots? The FlowNet can do it, or?
Well, when the FlowNet, it tells you how this pixel has moved from one frame to another. You physically splat that pixel on, and the remaining parts is just, there's a blank here. Let's inpaint that. The reason why I want to show this paper is because it shows how you can mix traditional CV and Stable Diffusion. And a lot of times Stable Diffusion is both a generator, but also just we have some problems with this traditional technique, but we can just fill it in with Stable Diffusion. And that's very cool, I think. Okay. Then we have AnimateDiff, which is from the same same lab as a T2I adapter. That Tencent ARC lab they're pretty cracked on Shanghai. But AnimateDiff, basically what this paper is they define this thing called a motion module that, again, kind of like Legion, where they inject it into the right after the attention layers. But specifically, what they do is they have this pre-trained Stable Diffusion model, And they just pass it in a bunch of images to train this motion module that instead does attention temporally. So it does it across the time dimension, which we would otherwise would not be doing. If we were to say with text and video, just generating complete separately, right? And again, zero initialized, same zero gating idea, right? It keeps coming back. But basically, what they realized is after they train this motion module, it can be inserted into any stable diffusion model that has Dream Boost, LoRa, anything, and it will work because it purely focuses on motion information. And that's why you're able to have stuff like looks like this, where it's a bit statically in terms of video, like it's not video. I would say it's more like anamorphs or like cinemorphs, I think that's the word. But like, it's very smooth. And it's like pretty convincing, you know, like the frame rate isn't very long because they trained this in like, I think like 25 frames or something, and that's like the max they did. But like, it looks pretty good, right? You're able to kind of replicate these camera motions and stuff like that. And all of these are different like Dream Boost / LoRa's. And they would work, and it would work on it. So, basically, yeah, generated videos can still be quite static, and it's not very robust, because I was messing with it a lot over the summer. It's not very robust. But, it works for if you just try to generate enough seeds, and if that one of them will work. So, that's a pretty cool result, and they actually got pretty, famous in the, like the Chinese, generative AI community. So yeah, you know, self-attention on the temporal dimension. Any questions about this paper? Okay. Then we move on to video generation for industry, where we got that big boy money, right? So first in September 2022, Meta made Make a Video, which is text and video generation without text and video data, which is pretty cool. And they started this trend of doing like for video models to do this almost like two-stage training, where they first train an image model on their text and video data, and then they train it then on video data that doesn't have text labels to it, with you know like additional modules and layers and you know that does this. And the way they do is basically they train spatial temporal decoders that basically takes our original like model, adds temporal layers to it. And they also add interpolators, which is basically they train text conditions, or like not really, they train text conditions interpolators to be able to take just a few frames to much longer, smoother video. And even though image quality could be better, it's very good motion for what it is, right? Again, not open sourced. And then NVIDIA came out with Align Your Latents, high resolution video synthesis with latent diffusion models. By the way, Blattman et al., this Blattman, also from LMU Munich, the Compass group. They basically single-handedly, almost stability started this whole like open source stuff. But this was a paper from NVIDIA actually. Basically it's video latent diffusion models that, the idea is we have this, you know, like latent space idea, right? In a latent space for image space. Why not have a latent space idea for time as well? That's what they did. It's a 5-stage process where you first generate your latent keyframes. You do in frame interpolation with a model. You do it twice, because why not? You have a model, do it twice. And then you decode it to pixel space with our new decoders in both. And the idea is that I think with Make a Video, they did like the whole like frame interpolation in image space, but they basically said, let's just do it in the latent space. It works well enough. And you can decode to pixel space, and then they also did another upsampler, so kind of similar to, you know, Imagen in that sense. But they also started with Stable Diffusion, or like some sort of text-to-image model, and just, again, injected temporal layers. But the difference between these and Animate Diff is that these took a lot of GPUs to train. Animate Diff only took, I say only took 32 A100 GPUs for like a day, which is like actually not that bad for all things considered. This thing takes much, much more than that. So yeah, that's pretty cool. Any questions on this? Yes, Maxine.
The idea is if it's latent in both like image and space, you can just like change tiny things and it'll look like smooth.
Yeah, and like that's kind of what latent frame interpolation is. It's basically you're doing all these within latent space instead of trying to do it in the image space. And then you have the thing that literally just came out about a week ago. Stable video diffusion. I'm very excited about this paper because it is literally align your latents with scale to 4 data, and the reason why you know this is because it's the same fucking first author. It's the same author from, again, LMU Munich. This guy, this is his whole thing, and the fact that he's able to do this, pretty good stuff. But like, and it's open sourced, right? It's image to video, it's trained on 14 or 25 frames, and it's basically align your latents scaled up to much bigger data. If you were to read the paper, it focuses a lot on data engineering, specifically on like how we can curate the data sets to do like multi-stage training, you know, like curate out, you know, specific data sets that are like, you know, this is higher quality than others, you know, stuff like that. And also it's open source. And also you can, and what they did is like, because they have this all like data engineering, you can actually fine tune camera motion LoRa's on, say you take a bunch of videos that specifically has a left to right camera motion, you can actually just fine tune a LoRa on that, and you can append that LoRa to any video, and it will replicate that camera motion. So that's pretty cool. But yeah, so that's video generation for industry. It came out literally just a week ago. I recommend you play around with it. Specifically, this one, however, does image to video. It doesn't do text to video. Because, which is kind of similar to what like, Runway ML has been doing with like their like, you know, I forgot like E2 or something, whatever it's called. But you can see how we can go from text to image to video very easily. We just generate a text to image first with normal stable diffusion. And then we just use that and feed it into this and we're good, right? So it says image to video, but really it's text to image to video. Though it does still have the sort of drawback of when it's getting interpolated into a video, because it's just image to video, it doesn't take in text information. So it's just looking at the frame and trying to figure out what's going on instead of having that extra text information. So it still has limitations on that. But it is already like much more robust than something like animative. Does this kind of make sense? Okay. All right. Then we leap into 3D. So we have this paper called Scenescape that came out around February 2023. And basically what this particular paper does is it tries to take advantage of the 3D, of again, the in-painting abilities of Stable Diffusion. Here's the pipeline. We first generate an image, right? We estimate the depth of that image. Based on this depth, we project this image into 3D space, right? Okay. We move the camera back. And as we move the camera back, there are areas within that image that is blank, right? We use Stable Diffusion to in-paint that. We do this extra optimization step that tries to match the depth of the previous step and this current step by optimizing the depth estimator specifically. We do this for every iteration to kind of match their depth. Using this in-painting thing, we estimate depth again, move the camera back, in-paint. Move the camera back, in-paint. Move the camera back, in-paint. We do this over and over and over and over again. And we're able to get stuff that looks like this. It's very cool. And they actually, because these are, you know, the first author came from computer graphics background, they also show the 3D view. It's great 3D consistency, and you're able to do this just from a diffusion model. That's kind of insane to me. Yeah?
Does this improve the depth estimator in general? Because it seems like a really cool way of like fine-tuning a depth estimator without any training data.
Oh, it could. Like just trying to make sure like these match. It could be. It could be genuinely a really cool way. Actually, you will see the idea of training new models from absolutely nothing, just looking at the knowledge of diffusion models in a little bit. And 2.4 diffuse literally anything. I want to make a callback to climate diffusion because now we have the idea of what diffusion models are. Looking at this, and hopefully it's a little bit clearer what's going on. I don't know who here was at Pratik's presentation on week 3. Okay, so we only know 2 people. I think Jackson was here, Leon's here. Oh, you weren't?
No.
That's so sad. But the idea of climate diffusion is that it is really easy to like find really global data. Like on the Earth, because like the Earth climate data is like kind of sort of regular in like at least a mean sense. So you can just kind of use regression to figure it out. But the moment you want to zoom in to much smaller scales, what happens is the kind of like the detail of the model becomes really bad. The resolution of the model of just normal regression is really bad because you were working on a much larger scale. The idea of a ResDiff, which is this climate diffusion paper, basically says this is our starting distribution. We're mapping it to our target distribution. Easily sampleable, aka just use our regression. Not easily sampleable, and it just trains a diffusion model to do this, and it works really well, right? Did it work really well, Pratik?
It worked pretty well. Also, the fact that like climate is stochastic and diffusion is also stochastic, so it's just good at like modeling that process.
Yeah, exactly. Like you see our good old like stochastic differential equation coming back again. 1982 paper. But yeah. Like another cool thing about math is just kind of like you sometimes solve things. You're like, sure, okay. You put it out, and like 30 years later, people are using your equations to do other things that you never thought could be possible. So I think that's pretty fun. So yeah, diffuse literally anything, and like this is the only slide that I have for diffuse literally anything. But you kind of see how like you can use this to do like 3D diffusion, like new paper that just got released. Where basically it does 3D diffusion directly in 3D. So they train an encoder in 3D. They train and they just diffuse directly into 3D. And I was like, for like given a bird's eye view image, 3D stuff. So like you can do this for literally any medium because the diffusion model, really abstract out, is just a differential equation solver. All right. Okay. Part 3, more than a generator. We're going to talk about things that are a little bit beyond what we're talking about right now, which is like different ways where the diffusion model is no longer just a generator. It is something else. And the first paper I want to talk about is Dream Fusion. Last time I gave the reading group, I tried to explain this paper very poorly. I think I can do a slightly better job now. To do that, we first have to talk about what nerves are. So nerves, or neural radiance fields, uses a MLP, or multi-layer perceptron, to represent a 3D scene, right? So specifically, what it does is you have this fully connected layer, right? Like just a bunch of fully connected layers, and you give it a few input parameters, x, y, z, theta, phi. Right? You give it these input parameters, you pass it into the model, and it outputs some RGB data. So, RGB sigma. Specifically, what's happening is this represents a camera view. You have this 3D scene. This is where the camera is looking at, and then this RGB omega represents the actual RGB values of the pixel you would hit if you were to do like a ray march to it, and then also the albedo, which is a fancy term for like reflectiveness for lighting. All right. So what they realized is, if you just train this on like a bunch of different images that the relative camera positioning to, you can create really, really accurate 3D models of the final one that's entirely captured within this network itself. So that's nerves. And at some point, I want to force our team to do a reading group with us. He also seems to want to do it as well. So we may talk about this in the future. But specifically, Dream Fusion takes nerves and goes, what if we train a nerve from 0 data and only diffusion models to achieve text to 3D generation? The way this works is, first, we randomly initialize any sort of NLP. So we randomly initialize our nerve, and we just try to render something with, lights and, a camera, whatever. And this whole process has to be differentiable because we're going to have to pass gradients through this. So we have to use what's called a differentiable renderer, right? So you do all this rendering, and then you design a random location for a camera. You take a picture of it, right? So you have this picture. So that's the first step. You first you use the nerve to render a scene at a random camera position plus lighting. You have this picture. Then what you do, you add noise to this picture, and then you pass in what your input text is going to be, and the diffusion model will try to diffuse that, right? Specifically, what the diffusion model is doing is it's trying to then it's calculating the loss between our predicted noise and the noise that we added. And what we do, it just back propagates that all the way back to the nerve, and that's our training step. And we do that over and over again, and you're able to generate stuff like that. And an intuition behind why this is the case is, for our predicted noise to match the injected noise that we added here, the image that we captured here must be in the diffusion model's output domain, according to our text prompt. So what the diffusion model is doing, it's really a critic. It's saying, hey, in order for my prediction to be right, here's the direction you should go in. And if the diffusion model's prediction is right, again, it's pre-trained, right? It's a pre-trained diffusion model that we're using. If the diffusion model's prediction is right, that means this MLP must be able to render a bunch, if we take snapshots of it, it must match what the object would actually be according to what the diffusion model thinks the object should be, right? So, if all this is successful, we have a 3D model that's being captured by the MLP. Now, this is very, very slow. It takes about 1.5 hours to train a single nerve on TPU-v4, which is like basically 4 A100s. It's very slow. If we were to do it on a normal lab server, I don't know if we would even have enough VRAM to do this, but it takes a long time. But it gives us a glimpse at what diffusion models really are, which is they are more than just generators in and of themselves. They are models that is able to capture information about the text and able to give information of how we can generate images that fit the text prompt. So it's a clip on steroids, because what people have done before is also they have tried to use a nerve, and instead of using a diffusion model, they just did a clip loss, which is like, does the outputs match the text? But they realized it kind of worked, but not really. But diffusion models, because it itself as a generator, has a stronger sort of information of how we can have this, generate information. So this actually worked decently well. There's been a lot of papers subsequently on this that push this further. I didn't include it because I'm personally not very familiar with a lot of the 3D stuff, but I think it's pretty cool. Okay. Then I want to talk about the comeback of GANs, right? So we very briefly mentioned Big GAN, which is, this paper is GAN, but big, that's what it is. And basically, people were making the arguments that GANs failed, right? Or like GANs weren't able to be scaled up. And that's why diffusion models took over. And to a certain extent, the diffusion model's ability to do self-correction is part of the reason why it was so successful. But what Adobe did in 2022 is saying, no, actually, GANs can just be as good as diffusion models. And this is GigaGAN. This is GigaGAN, and basically it's a 1.4 billion parameter model, which is about the same as Stable Diffusion. Stable Diffusion is around 1.3. And it is able to do text-to-image generation, higher quality than diffusion models, at higher resolution than diffusion models, because GAN's even easier to scale things up, especially since they were using a very vaguely style GAN 2 architecture. One-step diffusion, or like one-step generation. It's so much faster than diffusion models as well. And it has a very interpretable smooth latent space, because remember, style GANs are able to do that. So you interpolate between two images. It can do that as well, between two prompts nonetheless. And people say GANs are fitting to train, but Adobe basically showed, hey, it doesn't have to be. And this makes sense for them, because if you have noticed, and if for those of you who are unfortunate enough, like me, to be Photoshop users, you realize that recently actually started adding in what they call like neural filters, where you can do like generation and like in-painting and stuff like that. It's from this. Diffusion models will not make sense for them because it takes too long. Everything for them is processed on the cloud. But with GANs, it makes sense for them to do it because you just have to do inference on the model once. And it's about the same expense as passing through the diffusion model once. So this makes a lot of sense for the products, which is why they developed this and also did not open source it. But yeah, and there's this really interesting article. Yes?
I'm pretty sure Adobe Firefly is a diffusion model, not again.
Huh?
I'm pretty sure Adobe Firefly.
Oh, Firefly is actually a diffusion model?
Yeah.
That's rough.
Yeah.
Why didn't they use this? Oh, I guess like, with this they can do like in-painting and stuff like that as well. I don't know why they didn't do it, but it's a good point. Firefly is much more recent though. Like,
it says on their website.
Oh, never mind.
Firefly is a diffusion model.
I guess scans were actually being beat by diffusion anyway. But like my point is like Firefly is relatively recent, but then this was like 2022. And like I think for a little bit they did actually use this in like at least some of the beta of their products. Maybe it didn't work as well when they actually did test it. Who knows? But yeah, there's this interesting like article called GANs didn't fail, they were abandoned, which is like kind of true, where like GAN research kind of just like the moment diffusion became a thing, GANs, because it's easy to like it's like a little bit easier to train, and then people see a really clear path to scale it up. People just started doing it anyway. Like we have a lot of advantages with GANs, like, fast sampling, disentangle interval latent space, easy to sample from, precision rather than recall bias, and, better quality, usually text conditional, new tricks like classifier guidance, much stable to train supposedly. You can write a lot of papers about them. Noisy videos are fun to watch. Right? So it's like, there's some arguments that GANs are just as powerful as diffusion models, but the reality is currently there's much more research on diffusion models, and it seems like for scaling up, they're the way to go, especially with training-free research. You saw how we were able to just mess around with the attention layers of the models. Yeah. Also, another fun thing they did with this, the reason why it has so many parameters, is because they did another thing where they did like a weighted kernels, or like instead of just being like a 3x3 kernel every layer, for example, they had like 3x3, 5x5, 7x7, 11x11. They had a different bunch of versions of kernels, and they had a separate transformer looking thing that allows the model to select which kernel they want to use by weighting it. It's a whole thing, and that's why, and it's like, so you basically have this like really weird, huge convolution thing, attention, and that's why it's so huge. But that's what this model is. Just to pay homage to Benson a little bit, but artists fighting back. So recently, this is like October, someone came out with Nightshade, which the key is this. Nightshade is very interesting because the goal is to do data poisoning for diffusion models, where say I want to generate a bunch of text image pairs where it is clearly a photo of a dog. The poison text is clearly a photo of a dog, but if you fine tune this on diffusion models for even very few steps, it's going to start generating pictures of cats when you put a dog. How do they do this? The key is this. Remember intermediate features? Go back to it again. What they're doing is you have this image, and you have some sort of anchor image that you want to kind of like map this to. When you pass this image with this prompt through a diffusion model, it has a bunch of intermediate attention features, right? You want to try to perturb this image, FGS but fancier, so that those intermediate features match your anchor image. So, effectively speaking, to the model, there's no difference between passing in this image versus passing in this image. Does that make sense? And by doing so, you can screw the model up like this. And you kind of see how artists can try to use this to make sure their works don't get fine-tuned in the model. Because say, instead of mapping it to some sort of anchor image, they mapped it to pure noise. Right? So that's the idea. And it does require you to get the weights to diffusion models, to a model they're training with, but the reality is we do have access to those weights, which is very cool, right? Okay. Then we have some papers that's, to talk about beyond stable diffusion. SDXL recently came out from Stable AI, and they were, basically scaled up stable diffusion with higher resolution and an additional refiner that looks like this. It's much higher quality, and the kind of main contribution they did is a lot of data engineering, first of all, but also conditioning it on more things. Like there's a quality score they condition with, and there's a resolution condition. So basically, one of the original issues with Stable Diffusion is that they were training on really low resolution images that were blown up to 512 by 512. What they are doing in this timer instead is basically have these preset resolution buckets, and they basically condition the model, telling it, hey, this is the resolution of the image that you're actually training on, or the original resolution of the image you're training on. So when you're generating the final image, you just feed it a condition of really, really high resolution, so the image looks really high resolution. So the diffusion model is aware that, the current image I'm being trained is lower quality, but I'm gonna use it to learn things anyway, but keep in mind this low quality, so I don't want to, learn low quality stuff, if that makes any sense. And they also train an additional refiner that basically takes an output from a diffusion model and just does further refining to add details and stuff like that. And that's how they're able to get really good results. And also DALL-E 3 recently came out. Again, they released a paper that's finally a little bit more informative than the GPT-4 paper. OpenAI, but basically their main contribution is, hey, we can do all this architecture improvement stuff. That's all good. But the prompt is way more important. Basically, they showed that by changing these, because if you remember, a lot of these data sets, they're from alt text on the internet, right? Which sometimes describes the image, sometimes just doesn't. Sometimes it's just some random ad for Google PageRank crap, right? A lot of times the prompt doesn't match the image very well or doesn't describe the image very well. So they basically train another captioner to try to come up with really, really long and detailed descriptions that basically that matches the image really well, and they train a diffusion model based on that. And it looks marvelous. One of the things they show in the paper is that you're able to basically say list 100 separate things you want in the image, and it is able to generate all those 100 things in the image because it is trained to do so. So this is why, if you see literally the past two innovations has been on data engineering. So I think that's pretty cool. Okay. Now I want to talk about one last thing, which is something called distillation. The problem is that diffusion models take way too many inference steps, right? So how can we make it take less? How can we make it take fewer steps? With a lot of diffusion models, even with the best differential equation solvers out there, it takes 10 steps, 5 steps if you're pushing it for it to look decent. Any lower than that, it's gonna look like crap. This is where Yansong, the guy came along and proposed the consistency models. What these are is basically, they're able to do one step and 2 step diffusion really, really well. And the key is they're training the model to predict the same thing at all time steps t with a generalized noise scheduling concept. It sounds confusing, and it is, but here's the training. So basically the idea is you have 2 models you're keeping track of. For the process of distillation, specifically training a separate model to learn how the diffusion model is generating images, but specifically it can do so but with smaller numbers of steps. You have your target model, which is stable diffusion or whatever diffusion model that you have trained. And this is what you do. With the model that you're actually using to distill, the actual model you're training, you're keeping track of 2 copies of it. The first copy is the current model you're training. The second copy is an exponential moving average version of that model. So it's slightly lagging behind. What you're doing is you're saying, for a model prediction at t of n+1 here, when we pass in our x image, I want this to match what the target model is predicting at t of n+1 as well when we pass this back in. So we're basically making the model almost try to match itself in the EMA before. Right? So, again, this is what a target model predicts at t of n+1. So what's really happening if we were to look at this diagram again? It's the same. At any single point here, if this is one of our ODE trajectories, I have a point here, and I have another point here. I want the model to always point to the same place at the end. I want to always point to the same thing at the end, right?
So, sorry, I have a very quick question. Sorry, not related to this.
Yeah.
Sorry.
Okay, that's my grad student, Sichuan. He is the first author on the free control paper that we just saw. Little cameo from him. I was wondering, how do you know that I have a reading group happening right now? Anyway, so that's what a consistency model is. It's kind of confusing. It took me like a while to stare at it, and I still don't fully understand it. But the idea is that they're basically able to do this sort of one-step diffusion with this distillation method. And another thing they noticed is we can use a very similar loss, but instead of target model is just itself, and just train it from scratch. It's a lot more expensive to train it from scratch, like literally like 2000x the amount of to train a normal like DDPM diffusion model. Even I can do it. Like we can do it on like Pretty's laptop right now if we really try. Like on a 64 by 64 like SLEV A, which is like a phase data set model, to get a decent looking thing, you would train on that for like 16 hours, a day. You'll get there. So for this one, it requires, get this, 64 A100s to start, batch size of 2048, and it needs to train for quite a few hours. So like this is much harder to train, but it is able to do one-step diffusion directly. So obviously people then took that idea and applied it to stable diffusion models. Again, like this was for a separate reading group for my lab, so like it's a lot more. But then basically the main idea is, the main problem we have to solve is how do we actually take in account of classifier-free guidance with one-step diffusion, right? Because yes, we're doing the noise pushing thing, but like that doesn't make any sense when we don't have that iterative thing to help it, right? So essentially what they say is, we have this classifier-free guidance scale, let's just put it as part of it, and we just also randomly sample classifier-free guidance values to be like part of the model, basically. And that's basically how they train, and they have this other training loop that should, resemble the training loop of the consistency model, where they're basically saying, we have classifier-free guidance for the target model, and then we're using the latent consistency loss. Again, I don't mean for you to completely understand what's going on here, but the idea is that there has been methods which people have used and to, improve diffusion models. And technically, this is not even considered diffusion models. This is a new class of models because it has a different training objective. All the previous models we have looked at, like with the different formalisms of like, the SDE, they're all about inference, right? They're all about, we have this model. How can we take it from noise to image, right? However, the training objective is still the same. Predict the noise that was added. It's always been a training objective. We have changed the training objective this time. This is a different class of models that's very closely related with a lot of similar formalisms. It's not the same. Pratik.
Hypothetically, if you model perfectly converged and then approximated the score, would it not like trivially be a consistent model?
What do you mean by? Yes, technically for diffusion models, if it completely converges, aka the noise it predicts is perfect.
Yeah, if you know the score, then you have a consistent ODE trajectory.
Well, the problem is people tried that. They kept training diffusion models. None of them managed to converge at that point. So they had to come up with something else, and this is what Yang Song came up with. However, what we realized with distillation is Stability AI strikes again and says, actually, you don't need that. GANs are sort of back. Basically, the idea, they literally like 2 days ago, this is released on the 28th of November, right? This is literally 2 days. This is how fast diffusion model research is going. I want to reemphasize this. This is how fast it's going. 2 days ago, they released SDXL-turbo, which is training on two objectives at once. The second objective is we're trying to match the teacher XDXL level, which is the same as normal distillation, right? We're training this model to do one-step diffusion that fits what's the network we're trying to distill would be. But the first one is we're trying to fool a discriminator that the output x0 is real. And specifically, this discriminator is actually not trained jointly. I believe they actually trained this separately first to try to distinguish between the normal diffusion models is x0 and not x0. And it's also like further fine-tuned, if you will. So it starts out having the ability to do a decent level of distinguishing. But basically what they showed is it looks marvelous. This is raw one-step diffusion. It looks much better. Not much better, but like a decent amount better than latent consistency model that we just saw, right? And specifically, if you're wondering what one-step diffusion looks like for normal diffusion models, it's like this. Like, it doesn't look good, right? But this looks really, really good.
Is the ODE trajectory for this thing like consistent?
Well, there's no ODE trajectories anymore. You're just going directly, right? And you can also do multi-step diffusion if you want it, but you don't have to anymore. I think that's pretty crazy. Okay. So, what's next? we've looked at a lot of papers today, a lot of papers. And there's a lot of things that is yet to be done in this field of research. Obviously, there's a very big field of research right now, which is making text-to-image models actually runnable on mobile devices. Because on our phones, we have very limited VRAM and we have very limited processing power. So there has been a lot of work on pruning and trying to do quantization on the model to make it much more runnable on smaller devices. Specifically, Qualcomm has a whole series of papers doing this. They managed to make diffusion models, which is usually on floating point 32, runnable on int 4. Int 4 can possibly represent 2 to the power 4 numbers, 16 numbers in total, and they managed to make diffusion models work on that. It's pretty crazy. Obviously, there's a very big problem with watermarking models. If you notice, a lot of Stable Diffusion, if you just were to use the web UI, they do watermarking automatically, right? But if you actually look at the code, it's one code that literally says watermark, and you can just comment it out if you want to. So, there's no good way for us to watermark models right now. But so a lot of people are thinking, can we train the models in such a way that all images that it outputs is able to be watermarked? It's by default watermarked. Which then there will be people saying, can we unlearn that watermark? Machine learning is a whole field of adversarial research, right? So it's almost tug of war situation where they're constantly trying to outbeat each other. But that's a field of research that we also have to look at. Obviously, using diffusion models to solve very specific problems like medical imaging or climate data, people have realized that this is actually really, really good and just smash diffusion models on a bunch of different applications and it works. So has been a lot of papers based on that where they're using the ideal diffusion models to solve other, what we call inverse problems. Because remember, what diffusion models are able to solve is if we have a process that goes from point A to point B, and we know how to model that point A to point B process really well, what the diffusion model is able to do is take us from point B back to point A, right? So there's this whole paper called Diffusion Models for Inverse Problems, and that's what it focuses on, which is the idea that this is what diffusion models are meant to solve. The idea of, we have this process, can we invert it iteratively? And obviously, better video and regeneration. It's a huge field. Video generation is popping off right now. I don't know if Stable Video Diffusion was out 1 to 2 weeks ago, right? And obviously better 3D generation, which I'm not an expert on, but then, there's a lot of people working on that. And obviously, what's beyond diffusion models? We saw consistency models and we saw a glimpse of the future, but, stability basically say, yeah, we don't need that for distillation. But what if we can just train diffusion models from scratch with the consistency loss, right? I guess it would be a consistency model at that point. Do we need distillation? We don't know. But there's a lot of research that's definitely beyond. And I don't know what the next big thing after diffusion models will be for text-to-image generation, just generative vision in general. But I do hope that this little talk has given you some idea of what the current state of the field is. And maybe in the future, you can do your own research to figure out what's beyond diffusion models. Again, some acknowledgements, of course, from Professor Zhou for letting me mess around with this on lab GPU all summer. And also thanks to University Sciences for actually giving me the scholarship to do this during summer. Sicheng, who just left to take his TOEFL exam, good luck to him. He's MSCS working in Professor Zhou's lab, and he basically showed me the wonders of training free controllable generation. I joined the lab knowing what a diffusion model is, but not knowing half of this presentation. He showed me, hey, there's a lot of things you can do with it. And I think it's really cool. Thanks to Hanlon and also the Awesome Lab for letting me train my very first diffusion model. That's the first time I actually trained a diffusion model from scratch, and I did it on their GPUs, which was really cool when I was in their lab. And also for Pratik and Jeffrey for listening to me talk about this all the time. And obviously thanks everyone here, and also Jeffrey on Zoom. I don't know if, we have another participant on Zoom. Who is it? Nikhil is also on Zoom. Hi, Nikhil. Also thanks for everyone for coming. Thank you. Yes.
You see on Thursday, Stefano Erman's lab put out RLHF for diffusion.
No way. Wait, did they? Oh,
it's a published paper, yeah.
That's insane. Okay, I gotta look at that. For reference, RLHF is reinforcement learning with human feedback. So I guess they started out with a normal diffusion model that's already pre-trained.
Yeah,
and they basically
DPO
yeah, that's how they fine-tune ChatGPT, right? So with human feedback, that's insane. But yeah, one more thing before we go. Looking back at this quarter, we talked about a lot of things in Reading Group. We started out with deep reinforcement learning from our very own John Lin, who's researches on RLHF. We have Pratik and Ovid talking about climate diffusion and other climate things. We have Jeffrey talking about quantum machine learning, Benson talking about federated machine learning, and now I'm here talking about diffusion models. We have some plans for the future. So peering forward, I want to make Pratik talk about NERFs at some point because he seems like he really wants to talk about it, and maybe also LLMs at some point else. as well. We have like a few officers who I know are like pretty good at LLMs. Jeffrey's also pretty good at LLMs, and like I think pretty you have like worked with LLMs. Have you? Yeah. Jeffrey and our team are pretty good at it. Kevin is really good at neural AI, so he has been doing research for that for a while. I want him to talk about it, and also one of the co-authors of Stable Diffusion, who is actually UCLA students, will be coming and talking about how they built the thing around tentatively week 3 or after. So that's one of the reading groups that will be coming next quarter, and we have many more to come that's still kind of in the works. So yeah, thank you very much for coming. See you next quarter. Woo.